Okay, welcome back. So, in the last video, we estimated the weight of the atmosphere, that old windbag, and it turns out that it's heavier than you might think. 5 times 10 to the 18 kilograms to be precise. Over 5,000 times the mass of Mount Everest. So if a bit of air is that heavy, imagine what the oceans are going to weigh. A lot, right? So in this video, we're going to estimate the mass of the oceans and find out which weighs more, the atmosphere or the oceans. Okay, let's dive in. Get it? So, what do we need to know? I think this is actually a bit easier than the calculation of the mass of the atmosphere. All we need to know is how much ocean is there and how much does a bit of ocean weigh? Simple, right? So let's think about the total volume of the oceans. How are we going to go about this? Well, like in the last video, I want to make use of things that we already know. And a fact that is often repeated is that 70% of the surface of the Earth is covered in water. So let's take this as an initial estimate and we've got to start. And so then we need to know, how big is the Earth? What is its surface area? Well, conveniently, we calculated that in the last video. To briefly recap, we assume that the Earth is a sphere, the surface area of a sphere is 4 pi r squared, and we take the radius of the Earth to be 6,400 kilometers. And so doing that calculation, we estimated the surface area of the Earth to be 5 times 10 to the 8 square kilometers, or 5 times 10 to the 14 square meters. So then if we assume that 70% of that area is covered in water, we get a value of 3.5 times 10 to the 14 square meters, 5 times 0.7 being 3.5. And so now to work out the total volume of the oceans, we just need to know the depth of them, the average depth of all the oceans. Now, this is a number I don't know, but in the spirit of this video, we're going to estimate it. So I do know that shallow seas can be as shallow as a few tens of meters, and that the deep ocean is much deeper than that. How much deeper? I think some parts of the deep ocean probably go down to about 10 kilometers. So maybe we could go somewhere in between those two. And I think that probably most of the ocean is deep ocean. So perhaps we could estimate the average depth across all the oceans as, let's say, 2 kilometers. So the total volume of the oceans is then 3.5 times 10 to the 14 square meters multiplied by 2,000 meters, or 2 times 10 to the 3 meters, which gives us a total volume of 7 times 10 to the 17 cubic meters. Okay, now all we need to know is how much does all that water weigh? Well, from GCSE chemistry, I know that 1 cubic centimetre of water weighs 1 gram, assuming that water has a density of 1 gram per centimetre cubed. Okay, so if we just scale that up to 1 metre cubed, if 1 centimetre cubed weighs 1 gram, 1 metre cubed weighs, so we're going from centimetres to metres, so that's a factor of 100, but in fact we're going from centimetres cubed to metres cubed, so we need 100 cubed, which is 10 to the 2 to the power of 3. So 10 to the 6, or 1,000,000. So 1 metre cubed of water weighs 1,000,000 grams, or 1,000 kilograms in SI units. Or we can say a ton. A metre cubed of water weighs a ton. So before we're happy with that estimate, there's maybe 2 things we should consider. Firstly, does a centimetre cubed of seawater really weigh 1 gram? Is its density the same as pure water? And the answer to that is no, because it contains salt, which makes it more dense than pure water. But I don't think it's by too much, and so our estimate of 1 for the density is probably going to be fine. Maybe more important is the question, does the density of water change as we go deeper in the ocean? We know, just from a little bit of diving in the swimming pool, that the pressure increases as we go deeper in the water. So shouldn't the same amount of water get squashed into a smaller and smaller space as the pressure increases? Meaning that 1 cubic meter of water will now weigh more than a ton. Well, it turns out, no. Liquids are essentially incompressible at the sort of pressures that we're talking about, even at the depths of the ocean. Again, it might make a couple of % difference, but for our estimation, it's going to be fine. And if there are variations through the ocean column, these are more likely to be caused by changes in salinity or temperature of the water. Okay, so now we have a total volume of the oceans, and we have the mass of each unit volume. All we need to do is multiply those two together to get the total mass of the oceans. So we have our volume, 7 times 10 to the 17 cubic meters, and we're saying that each cubic meter weighs 1,000 kilograms. 7 times 10 to the 17 multiplied by 1,000, or 1 times 10 to the 3, gives us 7 times 10 to the 20 kilograms. There we are. The mass of the oceans, we're going to estimate 7 times 10 to the 20 kilograms. And now if we go back and we compare that to the mass of the atmosphere that we calculated in the previous video, we see that the oceans are a couple of 100 times heavier than the atmosphere. Now, you probably expected all along that the answer was that the oceans were heavier than the atmosphere. It's very much the intuitive answer. But I think the fact that they're only a couple of 100 times heavier is quite surprising, at least to me. So there you go. We've calculated the mass of the atmosphere and the mass of the oceans, and we didn't look up one value, and we didn't use a calculator once. We've made some estimates along the way, and maybe you'd even call our estimate of the ocean depth a guess. What's the difference between a guess and an estimate? And while this did in fact lead to a bit of error in our estimation of the total volume of the oceans, I think in problems like this, you've got to be pretty happy with only being a factor of 2 out. Okay, so thanks for watching. I hope you've learned something, and check back soon for more videos, or subscribe and let YouTube check for you.